Paul here, and we're now on part 3 of the LX64 ASM web server application. And if you watched the last video, part 2, you will know that I had mentioned that I was wanting to enhance the API capability before I release the code. I've done that, so we will release the code with this video. It'll be in the description in a zip file. We'll look at that in a minute. So what I did is I added some more. This was the default API body, right? You would type in /API and it would basically spit out this JSON file. But that was just a temporary placeholder, and I left it in the codes because it shows how you can actually output directly a hard-coded JSON string or any data. So I left it there for that purpose, and that is referenced by /API in the URL of the web address. And of course, every variable that you define, you have to also define the length of that variable. So you define a variable, and then you define its length. And you have to use both when you're sending data back and forth for header information or whatever. But I added 2 more. Now these don't exist, so /API/config doesn't really exist in the website. There is no page called config. It's just to the server, it's as though that was there. It doesn't matter. You could have a file, you don't have to have a file. If, for instance, we use .index.html, as a default. So it could be a real file, or it could just be a parameter that you're passing in. And since we're doing API, parameter works fine. So I created one called config, and I created one called report. And both of these, what they do is, in this JSON markup of this program, basically I wanted to show how it can read JSON and write JSON back and forth. So you can have two-way communication, which you would have to have, right, in API communication. So what I used as an approach is a markup of basically like the server config. So this would be like an administrator would come in and configure the server using this command, and he would send over a payload, a JSON payload, to configure the server. And then he would, at any point, he or she would ask for a report of the server's current configuration, and it would return a report. Now, there would be a whole lot more ASM code to actually communicate that with the kernel and get what we're actually going to show in a moment. But this is just to show how we can read JSON and create JSON, write JSON and send it back as a response. The actual things that we're telling it to config and the report we're getting back is just fictitious data, right? It's just to show the communication protocol. And so this program is now over 1,000 lines of ASM code, so obviously I didn't want to make it really long. It's long enough. So that all said, we have a few things, like we have the beginning of the JSON response. So if you ask for a report, the first thing it's going to, well, if you set the configuration, if you send in an API packet to set the configuration, it'll take that payload, parse it, and it'll come back, and if it has no problems, it'll send this JSON response, configuration updated successfully. And again, of course, anytime you have a string, you got to have the length, right? Because that's all part of the header communication with HTTP protocol. If you ask for a report, it'll use this prefix string, which basically says status running. Obviously, the server's running, or it couldn't even respond, right? So the first thing is the status of the server is running. And it starts with a curly bracket because that's the beginning of JSON, and then, you know, the length of the string. These are the parameters that we can set or read. We can configure these parameters, turn them on or off, or we can get the report of what these parameters have in memory. And so we have uptime seconds, how long the server's been running, requests served, the number of requests the server has served, number of clients, number of current clients or number of connections, and how much memory on the device on the server is being used by this application. So these are the things that we say, give me this, I don't want this, you know, for the report. Or we may say, I want this, I don't want this, or I want them all, you know, or I don't want any, I just want to know if the server is running, you know. So you got options here, and we're going to look at that in just a second. And so, let me close this find and replace thing I was doing a little while ago. So now you have these strings: set uptime seconds, set request served, set number of connections. This is where we actually set the configuration. So the administrator would come in and set the config state of the server. And then, of course, this is where we actually stop putting it back out. There's our login credentials to log in. And if they're wrong, there's the login failed. And let's see. Then we got some memory usage strings that we created here. Process ID, sides in memory, and kilobyte. These are just strings that we can build and send back into JSON. We're using a buffer. This is the buffer for the internet or reading files from the PC. And this is the request buffer coming in from the website. So we got buffers. Uptime, we have flags that are set here. And you can read these. I mean, you'll get this ASM if you download the zip file. And it has all the comments that explains this. Uptime flag, 0 is, if the flag is set to 0, it's false. We don't want that data. If it's set to 1, it's true. We do want that data. So do we want a report that has the uptime flag? If yes, we set this variable to 1. If we don't want the report connection flag, we set it to 0, and we don't get that. And it's 1 byte, because it only needs true or false, right? So it's basic logic, very simple, little memory consumption. And anyway, the code is in here. There's quite a bit. Like I said, there's 1,000 lines of code. And let's see, it's way down. It starts. Okay, here we check the API. And if we want the report, if the request is for the report, then we jump down to that section. We handle the post. Send a config success response message. This is where we send back to the client the actual report. This is where we generate the report. And we have to push these variables. Now, at the very top, we push some variables to the stack, and we leave them there. And here's where we can we push them, and that saves the registries that we're using. These are call save. This is where we store in these variables our flags, our 1 or 0, true or false. So each one of these are 12, 13, 14, and 15 correspond to well, what we want in our report, what the configuration is. And they're stored in these R registers, because the R registers are callee saved registers. We can control these registers. They won't be clobbered by system calls. They won't be overwritten. They'll stay there. And so, like, if you was writing a very basic program, like, say, BASIC program, an old BASIC program, right, on a 8086 processor or something like that, and you said, you know, A equals 5. Well, what you would be basically doing, what the processor would be doing, is storing 5 in a variable, in a registry, and then storing that on the stack. And that way it's a global variable. You can use it anytime by calling it. And that's pretty much what's going on here. We covered that in the previous video. So these flags are being interpreted, all of the subroutines here, pretty explanatory to explain what's going on. I don't want to go through it because I don't want this video to be as long as the last two. I just wanted you to see it. So now to get the server running, I'm going to go ahead and I'll show you the total length of the code. There we go. We got 1,394 lines of code. Of course, some of it spaces, but you get the idea. That's pretty good size assembly language application. So I'm going to start it just by using the debug panel here. We'll get it going. And so now it's running. I'm going to wait for a little message here. Okay, there it is. There's our code running. So here, of course, it wasn't running, so page not found. We'll refresh, and there's the login page. So now if we log in with our admin user, we come to this page, and I added server status. So basically I moved Google here, and ASM's still there. These links still open in a new window, and they're fully functional. But the server status opens up a new page called serverstatus.html, which you can see down here in the bottom left corner. So we click that, we get our warning that that's not a very good password, 1234. Well, we know that, right? Okay, so this is the dynamic admin page. This is where the administrator would come in and set the configuration. So these are the matrices that you can set. You can turn on uptime, request served, number of connections, memory usage. This is where you would choose what kind of report you want. You'll notice that when none of them are checked, it defaults to all false, none of them on. So if I run this now and I do, I set the configuration to all 0, it says the server responded back, the configuration was updated successfully. If I say, give me the report, this is the API string, the GET request that's sent to the server, and then this is its response. The status is it's running. Because we said we didn't want any other information. We just wanted to know that the server was running, you know, that it's actually functioning. Now if I come in here and I change these, like set uptime to true, and let's do number of connections to true. So we don't want the set request served. We don't care how many times the server has sent out a response to a client. We don't care about how much memory is being used. We just want to know about the number of concurrent connections, how many clients are connected, and how long has the server been running. So we set that. Configuration is updated successfully. We say get the server report, and there it is. The status is it's running. The uptime seconds is 150 seconds, and that's what we asked for. And the number of connections is 15, and that's what we asked for. We didn't ask for the others. So now if I come in here and check all of them, set the configuration. Now the configuration's updated. Get the server request, and there it is. And just so that you can see that we're actually running, let's go ahead and let's leave on memory and uptime. And we'll go to the ASP page here, ASM page. Scroll up a little bit, find where we actually have something. It don't matter. Let me just get down into the start routine. Okay, we'll put a break right here, right after that system call. Now, if I come in here and I click Set Configuration, the configuration is set. I get report. Oh, it's still running. Okay, hold on. Let's try again. I might have to stop the server and start it again. Ah, I was wrong. I needed to be over here. My bad. Okay, so now we get a breakpoint in the except loop. So let's try that again. We'll turn this one off. Just turn it back on just to get it to refresh. Set the configuration, and there you go. We're actually in the code. And we can step through the code. So you can see that it is running the actual ASM assembly, right? We're running the code. So if we jump over everything, well, hit continue, we come back, and there's the configuration set. We click get the report, comes back in, we hit continue, comes back with the report. And so this is just simulated data. Obviously the system is running, so that's actual data. Uptime, seconds, that might be right. I'm not sure. I don't remember how I wired that up because I did it at the beginning of editing code. But these I know are wrong. It has not done 16 things. Let's give it a good breakpoint. Continue. Okay, and then get. Now see it jumped to 18. So that's just a random generated number. 20. It's going up by 2. That's interesting. Huh. So it is recording it. Uptime seconds. Let's see what that's doing. Yeah. It is maintaining in memory, you see that, but it's not accurately counting. And this is definitely wrong. This is just a manufactured string. The process ID 1011. The process ID is changing. The memory 63,488. 64. This is definitely fictitious data that I'm generating in the code, and it's just to show that how it can read JSON. We're sending in a valid JSON, so we'll do a new one. Actually, let's just check them all. We're sending in a valid JSON, and it's responding with configuration updated successfully. It already knows we want these. Now it stores these in those R registers that we looked at. And so they're pushed to the stack. That's how the permanent memory is there. So when we do another thing like get report, these have already been set on the stack. It pops them from the stack and creates the JSON information. Okay, so the code is working. It's fully functional. You got a neat little interface here that shows you how it works. And I'm going to just close the browser here. If you go into the code, I documented, us developers, we hate writing comments and documentation. I didn't create a document. I just commented in here, but you get the idea. Now there's one other thing I wanted to go over, and that is this zip file. Yeah, this zip file. This will be in the description. So, no, it's trying to open it in the browser in there. Let's get that out of here, and we'll just open it this way. Okay, and I'll pull it over. This is what's in the zip file. There's a spreadsheet that I created, and this is something that'll be useful to you. But as far as the actual files from the app, we got the home page, the index HTML. We got the login page, which says, you know, that you're logged in, and shows you the Google link and the server page and all the other links. This is the server status page, or the server admin page, if you will. This is the ASM, the 1300 line plus line code, and then here's where it's compiled on my Linux machine, so you can run this. Did I stop it? That's a good question. No, I don't think I did. Let's stop it. If I bring in a terminal, well, I'm not going to do that. Basically, if you're in Linux, it'll probably run just, you know, cd into the directory and putting in /server. It should automatically run for you, but and it'll serve these pages, but these pages have to be in the same directory as the server. So I would just put all these in the same directory, and then it'll run. Or you can recompile it yourself. You can make changes, whatever you want to do. Now I created a spreadsheet, and we'll look at that. And let me shrink it down a little bit so it's within the video here. Okay. This is the system call commands for ASM x86 64 Linux. And so, like for reading a file, you would set rax to 0, and then it takes these parameters. So rax is your command for system command. That's what you use. And these are the opcodes that you would use for these. Like read is 0, write a file is 1, open a file is 2, close a file 3. You get the idea, right? The reason I put it in this spreadsheet, now you can reference this online, but it's just text and it's a long table. But I made this spreadsheet so that you can scroll up, find the one you want. Like if you wanted to do accept, you would put 2B, hexadecimal 2B in racks, right? And then you would set RDI, what was that, accept? You would set RDI, you'd pass an integer in. RSI, you'd send in the socket address, and RDX, the integer pointer. And then you would call system call. When you call system call, it would do the accept command. So the other reason I wanted to do this is so that it's easier, right? You can scroll around, but you can also sort. So you can use the data and sort by whatever column you want, right? So if you didn't want to sort by number or, you know, rax code, you could sort by the system call field, which is B. So you go to syscall, okay, and now they're in alphabetical order. So you can find what you want really fast, like here's exit, which is syscall 60. So you pass in 3C into rax, and you know, and then set, if you got an area code, you can pass it in that you want. If you want to put out an you don't need to. This is not even needed. These are not needed, right? Because when you do a system call 60 and then do it, set rax to 60 and do system call, you just sent in an exit command and the app's going to exit. So this is pretty cool because you can sort it that way. Now, the other thing, no, don't save. Okay, the other thing I did is if you're on, you know, if you use dual boot or whatever and you want to use XLS, which is Microsoft Excel. If you're booting in Windows or whatever, you can open it and you'd still have the spreadsheet, but it would be in Excel. It's the same thing, right? Or if you just want a comma-separated text file, you could click that and it would open in comma-set. Yeah, there it is, right? And if I clicked OK, it would open up in the same application on Linux. But yeah, if you just wanted comma separated, it's there. So I provide you with that as well. Now, if one last thing, if I open up the app again, get rid of that. And I come down to, let's find a SYSCALL. I should have just did a search. It would have been faster. There we go. So this is what I was talking about. Here's read. Remember, read is 2, right? So you set racks to 2. You pass in whatever the system call parameter is into RDI. You set ESI to 0. XOR X is basically just setting ESI to 0. You could just do move ESI, comma 0. But this is a whole lot faster and less work, less memory usage. So it's always better, if you need to set a register to 0, use XOR and XOR it against itself. And then you do the system call. So when you do the system call, you just now set this up for reading a file. Okay, so that's how you use it, right? That's how you can set up to do whatever you want. You just find what it is you're trying to read. Like here, we're setting it up to get ready to read a file. Now we're actually reading a file into this buffer. And so you set the file name and all of the variables that you need in order to read the file, and then you do the system call again. And this time it writes the actual file buffer, the text of the file or whatever it is, into this buffer up to this amount, right? And then to close the file, same thing. If you looked up close file, it would be racks, set racks to 3. And then of course the file handle, right? Because you've got to tell it what file you want to close into RDI. Same thing here, you tell it what file you want to open to read. Call the system call, closes, right? So you should know that. I mean, that's basic assembly. This is an intermediate assembly course. So if you're just learning assembly, this will give you some idea of the syntax and how the app processes through the code and what's going on. But to actually make changes or understand it, you should be an intermediate level assembly programmer on a Linux machine. Now, why Linux? Why didn't I do this in Windows? Well, that's the last function point I want to make. In Windows, it would be easier, because in Windows you're using Windows libraries, right? So you don't have to do so much of this. The code would be shorter to do the same thing. Not a lot shorter. But if you want to learn ASM, Linux is the best place to do it, because there is no shortcuts. You can't bring in printf, or any other library from Windows or anything like that. And it doesn't automatically handle the syscalls in Linux. You have to manually set it up and call the syscall. By doing this, you're learning assembly language much better. Sure, it's a little more work, but it isn't really that hard. And you're learning what's going on as you use it. Here again is another example of XOR, right? Setting it to EAX to 0. Moving the buffer into a string so that you can, or a pointer to the file into a string, so that you can actually loop through and find characters down in internet to ASCII subroutine down below, or skip extra lines. And there's a lot of macros in here too. If I scroll down, That's not scrolling, Paul. Try again. If I scroll down, you'll find a lot of macros being used, and they'll give you some good ideas on how to improve. Here you go. Like these. These are macros. These that you can create. And so this one is to set up a skip white space in the JSON file. So it uses the skip file flag here. And so this is really good stuff. We're using the haystack to set up the beginning point and then call find substring and jumping down and looking for information and skipping it based on these settings. And they're set at the top of the file as well, up in the data section. No, sorry, the bash section. So you got all of these variables and macros that you can, here you go, here's a bunch of them. So these help you understand what's going on when you're actually jumping around. This will help you understand what is going on, what it's doing, how the app is working. And the more you familiarize yourself with this, I was trying to find an actual code, but I can't seem to find what I was looking for. I apologize for that. But anyway, as you learning what these functions and doing the subroutines, these call statements and these macros, how they're functioning, how they work, you're going to learn what you need to know in order to actually not just understand what the code's doing, but to be able to actually write the code. And that's the goal, right? That's what we want to do. We want to learn not only what it's doing, but how can we manipulate the code? How can we change the code to make it do what we want to do? As you understand the logic of it and how it works, then you're able to actually start writing the code. The best and easiest place to start is get to know how these syscalls work, how you pass the variables in you want, and then call the syscall to do what you want. So this one creates the headers for JSON response, the HTTP headers that are sent to the client. And so, how to search through a binary string and an integer, right, and transfer it to ASCII in this function, the subroutine down below. When to pop and push and pop variables, which variables to use. All of this kind of knowledge will help you understand how to write the actual code. It's really not that difficult. It's just, it seems difficult because you got to do so many things, right? It's ASCII. It's not a high-level programming language. The other side of knowing this, even if you just want to know the basics of assembly, is for decompiling. So if you got a high-level application, you can decompile it using a decompile app and get it to ASCII. And then once you get it to ASCII, once you get it to assembly, then you can understand what the code is doing, and you can work with high-level apps and see how they're actually running on the PC. Because it will, when you decompile, you're going to get the assembly equivalent. And these functions are neat. You notice there's not a lot of syscalls here. The code, you're actually doing this yourself. I just find it so fascinating because you're manipulating the actual registries that are in the CPU chip. You're right down at the hardware level. You are controlling the processor. You are in control of the hardware. And that is so cool. Now, when you use syscalls, okay, what's happening there is you have to deal with the Linux kernel too. And the Linux kernels, there's some things it's not going to let you do because doesn't want to allow you to mess up the actual PC, right? Or mess it up and, blue screen in Windows, right? So the syscalls is an abstraction layer between the hardware and the Linux kernel. But you see, there's not many syscalls here. And so you're actually directly controlling the hardware here without using the Linux kernel. You are in control of these actual registries and these memory spaces yourself. I think that's just incredible. It's a great knowledge to have. I learned a little bit of this, not much, but a little bit of this when I first started programming, and that was in Fortran 4 using punch cards. So we're talking a long time ago. And of course, the assembly then was a little bit differently arranged, but it helped me so much understand what my Fortran programs were doing. Then when BASIC came out, I started playing around with BASIC on a microcomputer, and I understood what BASIC was doing. I understood what DOS was doing because of the assembly language knowledge. And now when I program in Python or C or C++, especially C, Linux kernel is written in C. So these all map directly to the C commands. So it helps you understand what the high-level programs are doing, and at the same time it gives you the joy of actually working and manipulating the registries on your processor. That's just really cool. I mean, you may find some apps online that tell you how to make a web server in C, or how to create a web server in C++, or C# or Python maybe, but here we're creating a web server in assembly language. You can't get any deeper into the roots of the hardware than that. And if you can pull something off like this and understand it, someone comes and says, oh, I wrote a server application in, Pascal or COBOL or anything, C++, or .NET, you can say, oh yeah, well, I've done one in assembly. I mean, that's like, selling apples versus the farmer that grows the apple trees. I mean, it's massive difference when you know how to do this. And it makes your high-level programming so much more better optimized. You write better code because you know what the compiler is doing. You know what happens here. This is simplified code. It's got to be right or it won't work. And so once you understand how this stuff functions, as you're writing regular code, you're less likely to write bad code. You're less likely to leave memory leaks in your application because you're already going to know that you got to do these things. Now, some of the stuff is done for you, like in Python, if you close a program, close a file, you don't even have to specify that you're closing the file. The file gets closed automatically. That's cool. But knowing that you have to close the file lets you know to check that, to make sure there's no memory leaks. Clobbering. Clobbering is when you overwrite your memory in a memory location because you didn't count the bytes correctly. You didn't move exactly where you needed to move, in your add and subtract routines. And when you clobber things, you got to understand, sometimes it's a system call. This routine here clobbers RBX, RCX, RDX, RDI. You got to know, these got to be pushed to the stack before I call this command, because IOTA is going to clobber these registers. So any values you got in there, you got to back them up. You got to push them to the stack. Then once you're done running the program, then you got to pop them back. So to get your information back. So clobbering is an important thing, and that helps you understand when you're writing high-level programs, what's going on with those variables that you're creating, those class files, those methods, what's happening in the background, what's really going on. You write better class files. You write better code all the way around. Anyway, I killed a dead horse, but this is all available for you. It's all in that zip file. You'll find it in the description, and I hope you enjoy it. If you have enjoyed it, please consider liking and sharing and commenting. Anything to help me, I would appreciate it, but that's your call, and I will try to make some more ASM applications, probably a little bit less complex than this, as we go forward. Write some routines or some utilities that you'll be able to use. And a lot of these you can compile and call them in your C programs or your C++ programs. Or Linux, Python, whatever. All right, thanks for watching.